Here we go. Good morning to everyone. Welcome to our session. My great pleasure to be here today. I'll be talking about the inclusion of plastic strain effects on cleavage fracture, toughness prediction using subsides pre-corrected Sharpie specimens. Here, okay. I promise to be very fast. Okay, so just go very super fast over the presentation. If you have some questions, you can ask me later. Since our chair is keeping things in a very high tension. Okay, this is the outline. I'll just briefly introduce you with the issue of fracture toughness in reactor pressure vessels using fracture specimens. Brief overview of the web stress, which is also known as the Vernier model. Inclusion of plastic strain effects. So the proposal of a modified web stress model, or a modified Vernier model, if you will, and the application to predict the specimen geometry effects on fracture toughness for a standard A533B pressure vessel system. Okay. So very briefly, that's the issue with the integrity assessment in reactor pressure vessels. So the steel become progressively brittle because of neutron radiation, especially fast neutron radiation. So the assessment of material degradation over its operational life is essential to guarantee the structural integrity. Okay. So traditionally, conventionally, this is made by using in surveillance standard or conventional surveillance programs a 10 by 10 Sharpie specimen. So this is a Sharpie geometry testing 3-point bending. So these are 10 millimeter specimen, and the goal here is to assess the structural integrity for a vessel which has 150, 200 millimeter thick. So the scale is very different. So the problem with the PC, the pre-cracked Sharpie specimens is that under bending or under loading, they will display large amount of plasticity before fracture and consequently constraints, which complicates the issue. So one of the possible approaches is to using a micromechanics model incorporating the statistics of microcrack. Okay, this is the base of the wide stress model. So we saw yesterday Professor Panetta here presenting phase field modeling. It's a very elegant procedure. There are other procedures to do this. The wide stress model is a simple procedure, but it's still highly effective. So that's what we would call an engineering level procedure. Okay? And the base here is that we can, in a very simple way, incorporate the key aspects of fracture, and also using a finite element analysis, really very standard finite element analysis. So again, very quickly, okay? This is the let's say the fundamental of the approach. So we do incorporate the statistical microcracks using a Poisson process. That's the basis. I know that some of you may disagree with this. We can talk about this later, but that's the basis. So we have let's say fundamentals to use a Poisson process to assume, and then by using a ad hoc microcrack distribution, we can arrive at and using weak link assumptions, we can arrive at a Weibull distribution for the fracture stress, okay? Where the Weibull modulus is the key parameter. What the Vernier many years ago did, the Vernier group, actually, so Pinot and many years ago, was to coin this fracture stress in this concept, the wide stress, which can be seen as a probabilistic driving force. So it captures first the statistical microcracks, the microcrack distribution, and it captures the actual stress distribution ahead of the crack tip or inside the fracture process zone. This doesn't not necessarily relate to the plastic zone. Okay, usually this is the process zone is taking us 2.5 times the contour of the principal stresses, which defines then the process zone. Okay, this is all good. So the Vernier model has been adopted for many years with relatively success. But the thing is, as actually we saw this in previous presentation, there is strong effects on plastic strain cleavage microcrack. And one of the drawbacks of the conventional burning model is that it assumes that all microcracks are nucleated immediately upon yielding, which is not true. Okay? Microcracks will nucleate as yielding progresses. And this will change the microcrack distribution and also as well the local crack yield. Okay? So we need a simplified approach, and that's what we did. So we went back to the Poisson process, to the fundamentals, and then we said, okay, how about assuming that only a fraction of those microcracks that for ferritic steels are usually carbides at the grain boundary. So many carbides at the grain boundaries under the action of plasticity will break, eventually become a microcrack, but not all of them will actually take part in the cleavage process. Okay? So we came up with a modified white stress, which does incorporate here the fraction of eligible microcracks which affect the cleavage process. Okay, and in our previous work, we have used a lot of some distributions for the fraction of eligible microcracks. And in this work, I'm using a Weibull distribution to describe the fraction in which one of the key parameters is the particle fraction distribution. This derives from one of the previous Wallenstein models here, which is called the WST model. In the paper, you are going to see the reference. Okay, that's the name. Okay, so that's what we're going to do with this model. We are going to predict the fractal toughness for the nuclear reactor pressure plus steel, okay, which comes from the commission Shoreham nuclear power plant. This is was in New York State. Then we're going to calibrate the Weibull stress model, which is the key parameter, and then we're going to predict the distribution of a large specimen using the subsized pre-crack Sharpie specimen. This is the material data here. So it's a standard A533 grade B steel here, the yield strength and the ultimate strength for the various test temperatures here. And this is providing the paper of Redmond and Odet, Eugene Fractal Mechanics 2006. Okay, these are the Weibull distributions for the data. First, you can see here the CT specimen, 1T, it's 1 inch or 25 millimeter thick, A over 9.5. This is the pre-cracked Sharpie, standard pre-cracked Sharpie, A over 9.5. And these are shallow cracked pre-cracked Sharpie specimen. You can see here that scatter does not fit quite well a Weibull distribution, but the most important parameter is the, let's say, the J0 in the Weibull distribution. Okay? And this is the second set of data here. So again, this is the CT, just to give you a comparison here. So this is the half pre-cracked Sharpie, so 5 millimeter thick. And this is the 1/3 pre-cracked Sharpie. Okay, it's 3 millimeter. So what we're trying to do here is to predict the toughness distribution for the CT specimen from there, the reference temperature, all other parameters, from a very tiny specimen, so 3 millimeter specimen. Okay, and so that's what we did. Okay, these are the Weibull distribution, not the Weibull stress distribution. The Weibull distribution, standard Weibull distribution for the toughness data, using a fixed Weibull module of 2. Okay, I don't have time to go into detail, but there is a mechanistic reason for enforcing a fixed Weibull module. This is related to HR, stress fields, and other things that we don't have time to discuss this. This is the key parameter here. This is called the character toughness. It's very close to the average. Okay, it's not quite the average. Specimens with different geometries. For this case, the calibrated Weibull module is 16. It's actually very close to what's around for structure steels, between 10 and 20. That's a very good number. Okay. And we also run the calibration for the particle fracture stress. Again, the same procedure. From scaling, using the toughness scaling procedure from the CT to pre-cracked Sharpie spent weight over that 0.5. And then you can see here that it's close to 1,800, something like that. Okay? So once the parameters are calibrated, what you do is just conduct a finite element analysis and run the toughness scaling methodology again. So this is the prediction. I'm almost done. This is the prediction with the 90% confidence bounds for the CT specimens predicted from the Sharpie, prepared Sharpie with 5 millimeter. You see very good prediction. Of course, the scatter, only a few points. The scatter is a little bit higher than desired, but still almost all data within the confidence bounds. Okay, you can see here the particle distribution is 380, 3080 megapascal, and the prediction from the 1/3 prepared Sharpie specimen. It does a very good job in predicting almost the entire toughness distribution for the CT specimen. Most of the data, or a reasonable number of the data, is within the confidence bound. Okay, and then what would happen if we used the standard Burden model? You can see here the predictions are way off of the actual prediction. And that's because, so this is the prediction from the 5 millimeters using the Burden model, and this is the prediction from the 1/3 by Sharpie using the Burden model. And that's because the Burden model does not capture any plastic strain effects on the microcracking process. Okay? And just to finalize then, okay, I promise you I will be very fast. Okay? The standard Burden model in many cases under-predicts the distribution of JC values or other toughness values. Okay? The inclusion of plastic strain into the Burden model, or the volume test, plays a very strong role in fracture predictions for the test of fracture specimens. We have done other cases, is essentially the same behavior, more or less, with more or less accuracy, but essentially the same behavior. Okay? And the predictions are very good doing it. I took out the other slide what was about ongoing work. So just to mention that one of the, let's say, one of the problems or the limitations with the modified volume stress model is parameter calibration. Okay? So what I was going to finalize is that we do need a simpler and more robust way of calibrating parameters. Right now is a little tricky and a little cumbersome. But anyway, if you get it right, the predictions are right. Okay? And thank you very much.
Again, we have time for one question.
Thank you for your presentation. In the brittle part of the transition region, are the simple bearing model and the modified version are equivalent, or?
No, they are not equivalent because the standard Burden model does not consider any plastic strain phase. So let's say the form, perhaps the form is the same. The closed form is very simple. Okay? That's why, for example, we can use the same code. You just have to plug in the plastic strain effects. Okay? You don't need much modification. That's the main advantage of this. It has some limitations, but the main advantage is that you can use the same framework for the Burden model. You just have to plug in the evolution of plastic strain in each element around the previous. They are very simple.
Okay. Thank you.